This example is dedicated to the Biot-Savart law and the magnetic field superposition principle. The Biot-Savart law states that the magnetic flux density vector at any point could be calculated using this equation. Here, I denotes the electric current value, L vector points in the same direction as the electric current, and the magnitude of this vector is equal to the conductor's length. R vector starts at the conductor carrying the current and ends at the point of interest. And R scalar value is equal to the distance between the conductor and the point of interest. And mu 0 is the magnetic constant. Now, next, the magnetic field superposition principle states that we can compute flux density vector components independently from different sources and then add them to find the total value of the flux density. So in our example, we have two straight conductors. Our task is to calculate the flux density vector components at the point K. The distance between conductors is 1 meter. The conductors carrying current of the same magnitude but in different directions. And the point of interest, the point K, lays just above the left conductor. And here you can see the components of the magnetic flux density vector calculated using the Biot-Savart law. B1 is the flux density induced by the left conductor with current I1, and B2 is the flux density induced by the second conductor. Let's simulate this case with QuickField. I create a new problem. The problem type is magnetostatics, and the conductor's length in the z direction is 1 meter. It is presumed that conductors' diameters are small comparing to the distance between the conductors and the distance to the point of interest. We can simulate this by adding conductors with zero cross-section. I will add this point, and this point will represent the left conductor. And here will be another conductor. And I will also add the point here. This will be the point of interest. And the magnetic field will be distributed somewhere between the conductors. QuickField cannot compute the magnetic field distribution in the unlimited area, so we should add the boundary. This would be the boundary. Now the geometry model is and R should assign labels to the geometric objects. I switch to the Select Objects mode, click the object, and open the Properties dialog. Here I type in the label name, Air. This would be the boundary. Now this is the left conductor, I minus, this is the right conductor, I plus, and this is the point of interest, point K. Once we have completed the geometry model and label assigning, we should specify the physical properties for each label. I double-click the label name in the tree, and in the dialog I specify the magnetic permeability of the air, which is 1. Far away from my conductors, the magnetic field fades to 0, so that at the external boundary I specify 0 magnetic potential. For the left conductor, I specify the linear current, minus 10 amperes. For the right conductor, I specify positive current, plus 10 amperes. And there is no source, specific magnetic source in the point, so I leave both options unchecked. Now I can build the finite element mesh and run the simulation. Let's zoom in. You see the field picture doesn't look nice. That's because the finite element mesh is not rightly sized. When QuickField builds the finite element mesh, the logic is simple. For large objects, the QuickField chooses large element size. For small objects, small element size. Once we have the results, QuickField can do better. It can automatically adjust the mesh size to get more accurate results. All you need is just to press Solve and Refine button. You see the mesh was automatically adjusted. And here we can take a look at the results again. Now the field picture looks much better. But if we zoom in more, we can again see the sharp corners. So I will repeat the refining. Now the result looks good. And my task is to calculate the flux density vector components in the point of interest. In QuickField, it's called the local values field parameters. So I specify the coordinates of the point. This is 0 for x and 0.5 for y. So this is the point, and these are the components. And you see the results are the one that we expected. The horizontal component of the flux density vector is 3.2 microtesla, and the vertical component is directed down with the magnitude 1.6 microtesla. You can download the simulation files following this link from our website. Here is the page. You can see the description of the example, and at the bottom of the page is the download link.